We are the Military Standard 1553 Communications Bus Analyzer Team for NavAir. In overview, we needed to design a bus analyzer that was able to capture live 1553 transmissions, convert them to hex values, and store them onto an external hard drive via a CSV or text file. The end goal was to assist in testing equipment such as with avionics or ECAS. The overall system needs to be portable, standalone, and robust. It needs to be able to connect to existing equipment available. The entire project was surrounded by the military standard 5053 protocol. This is a 1 MHz frequency protocol that's used amongst avionics equipment. It is a bipolar Manchester encoded signal, and it uses 3 bits for syncing, it uses additional bits for data, it uses further bits for addressing and other purposes. There are 3 different kinds of words that are used amongst the 5053 protocol, and that's a command, data, and status word. Between these different transmissions, there would be a 4 microsecond delay and therefore presents how fast the protocol actually works. In total, there's 20 bits per each transmission, and it's used for communicating to different remote terminals amongst the entirety of a jet or other avionics equipment. To successfully create our bus analyzer system, we first needed to create a bus coupling system. This coupler is utilized to tap into the coax cable lines that are used amongst ECAS and avionics systems to transmit the 5053 protocol signals. First, we had to create this coupler to transform the data into a much more manageable voltage range for our electrical systems. These electrical systems then transceive the data, store the data into SMS RAM, and then send the data off to our microcontroller. Microcontroller then is able to interpret this data and use SPI to send this data over to our external hard drive. So for the electrical design, we have different level shifters, transformers, and chips to receive the data. And for our software design, we have different accessing data protocols such as SPI, I2C, and utilize FAT32 or exFAT for the file systems of the external hard drive. Our microcontroller is coded in C and utilizes a 16 MHz clock speed to be 8 times the speed of the actual 5053 protocol clock speed and keep up with the data rates that it provides. The data will then send from the microcontroller to the external hard drive. For preliminary testing, we've prioritized testing our SPI communication to be able to access data and send the data to our hard drive. And then we are planning to simulate the actual 5053 inputs and then finally test the individual channels to write to our equipment. Our future plans include creating a sturdy housing as shown with a friendly interface on the CAD drawing, then do some additional testing for software designing, and then finally create a PCB board design after our prototype has worked.